cross divide, okay, and we're at a estimated population size of 70. Right. When we're also studying populations, we'll look at what are called survivorship curves. There are 3 different types of survivorship curves. The first one would be a type 1 curve. And a type 1 curve is relatively flat at the start. Okay, so when it's flat at the start like that, that means there is a relatively low death rate. So you can see down here, you've got percent of the maximum lifespan. So in this type 1 survivorship curve, it's a high percentage, okay, that are making it further into this lifespan. And you don't really see start to see a decline until about 3/4 of the way through the expected lifespan. So there's a very low death rate. It's a high rate of survivorship in the beginning, which means, though, that there's a large investment in the offspring. These organisms usually have fewer offspring, and they take a lot more time and resources to take care of these offspring. Okay? And you don't start to see an increase in the death rate until they're older. There's a type 2 survivorship curve. A type 2 survivorship curve is pretty steady. You can see it going down here. It's pretty steady, which tells you here that I've got a relatively constant death rate. Okay, something that you guys are going to need to remember for this class, okay, is that something you know from algebra is that rate is equal to slope. You have got to remember that rate is equal to slope. And so I have a relatively constant slope here, which means I have a relatively constant death rate. Okay, your type 3 survivorship curve is this one here on the bottom. And you notice it has a very high death rate in the beginning. Very, very high death rate for the young. But basically, once you reach what's called a critical age, there's a high survivorship now. And so the example they show you there is oysters. Oysters, basically, once they are old enough to fully grow in their shell, they have a pretty high survival rate. But these organisms then usually produce many offspring. They don't really have that investment in the offspring. So lots and lots of offspring, but they don't really care for them. They don't really provide them with resources or try to ensure their survival. We also have what are called population growth curves. So we saw survivorship curves on the last one. Okay? These are population growth curves. And so with a population growth curve, you can determine, you can work on births and deaths and determine the changes in the actual population. Like for instance, if you look at this graph, if you look at how many more, you've got your population on the y-axis here and you have the year here. So you could determine how many more deaths occurred in 2001 versus births. And so you look at your population in 2000, which was 16,000. You look at your population in 2001, which is 12,000. So you have a decrease or a decline of 4,000 between the 2 years. So that tells you that there were 4,000 more deaths than birth. It does not tell you that there were 4,000 deaths, but it tells you that there was a difference in the birth rate and the death rate. For instance, if you came and you looked at 1998 to 1999, you have 13,000 to 15,000. So now you had an increase of 2,000. So you'd have 2,000 more births than you did deaths. So when we're looking at population growth models, we have 2 basic models. The first one being exponential growth, the second one being logistical. You guys have seen both of these your freshman year. What we're going to do differently with these is we're going to be applying some math to these. Okay, so remember your exponential growth. This is that J curve, okay, where you have unlimited resources. the ideal population is multiplying rapidly. This cannot continue forever. At some point, there is going to be an issue with the resources and space and food. At some point, this is going to have an impact on the population. But you'll see exponential growth in the shape of this J curve here. If you remember from your freshman year, a lot of times you'll see the graph that will eventually even out. When we're looking at this mathematically, we're talking about our change in population over our change in time. So D is change, capital N, that's our population size, if you remember from the last equation we looked at. T is time, and that's going to be equal to what's called R max times N. And R max is going to be our per capita growth rate. We are going to, anything math related is one of the few things that we are going to talk about in class. We'll go over examples, we'll work problems in class. Right now I just need you to have some idea of where we can apply the math and just the fact that you're going to see it in general. So R max is our maximum per capita growth rate in what's called an R-selected or opportunistic organism. It's going to have a very short maturation lifespan, lots of offspring, early reproduction, and you're going to see this very rapid growth rate. Because remember, this growth rate here, this R max, is not limited by resources. So let's look at the kind of organisms. Let's look at the R species that can do this. These organisms here are examples of what are called R-selected or opportunistic organisms. And what that means is that these are going to grow with that exponential growth usually. They are going to have a very, usually a short lifespan, and their maturation will occur very easily. They will reproduce very quickly. It won't take long for them to get to reproductive age. So short lifespan, they're quick to reach their reproductive age. They're going to have lots and lots of offspring. These are one of those organisms that have large amounts of offspring, and so there's not a lot of parental care, if any, in these kinds of organisms. So not much of your parental care there. They have a very high death rate. Like I said, they reproduce early on. If you remember when we talked about survivorship curves, this would be a type 3 survivorship situation, where once they got past a critical age, you saw lots of them were living, but in the beginning there was a high death rate. Because again, they don't have a lot of parental care, they don't have a lot of resources to them, and they are on their own. So your logistic growth is the other population model. This is the one we use the most your freshman year in your biology class. With logistic growth, population density is taken into effect here. These are the ones that, after a period of time, even out. Remember, they reach what is called their carrying capacity. And if y'all remember, your carrying capacity is that basically that maximum level that the population can, that the resources that are there, that can be supported, that can support the population. So it's the maximum population size that the resources allow support for. So in this logistic growth model, carrying capacity comes into play. And you'll notice that in the beginning, these organisms were experiencing exponential growth. Remember, like I said, as a general rule, exponential growth cannot go on indefinitely. At some point in time, density-dependent factors are going to become an issue. The fact that there are so many organisms in one place is going to become a problem. The equation for this one looks like, so the change in the population size over the change in time, this is equal to that growth rate. So our per capita growth rate, and then we factor in the carrying capacity. K represents carrying capacity. So we're factoring in that carrying capacity here in this mathematical equation for logistical growth. And again, we're going to work with this in class as well. Okay, so let's look at the organisms that do more of this logistical type growth. The organisms that exhibit logistical growth are called K-selected organisms. They are K-selected because remember K represented carrying capacity. Okay, so these try to maintain a state basically of equilibrium. So these are also called equilibrial organisms as they're trying to maintain that kind of constant carrying capacity level. So these are basically the opposite of the R-selected species. So they're going to have a long lifespan. Usually it takes a little bit longer for them to reach reproductive age, where your R-selected species had a short lifespan. They reach reproductive age early on. These usually produce few offspring, and the ones that they produce are usually very large. You know, R-selected species may produce thousands of tiny eggs, where a K-selected species may produce 2 cubs. Okay. They also have a significant amount of parental care. They invest resources in their offspring to ensure their survival, so they have a low death rate. Remember, again, on our survivorship curves, this would be a type 1 survivorship, the kind where initially there's very low death rate until they reach, basically until they get old, and then you start to see a relatively rapid decline. The last thing we're going to look at on today's video is the environment and how the surroundings can impact the population, whether they can influence or have a positive, negative effect. We're going to look at a variety of examples. So the first one, some of you guys may be familiar with this, especially if you have gardeners in your family. It would be hydrangeas. These are the particular flower up there. And when the soil acidity is changed, that can affect the color of the flower. An acidic soil leads to a more bluish color. Okay, so the more acidic the soil, the more you get this bluish color of the flowers. And the less acidic, as the soil becomes more neutral, you get these lighter, pinker colored flowers. So the soil acidity can have an impact on the flower color. Okay. Another example over here in this diagram here, you can see with these fish. Okay, so with fish, as they are swimming around, as they change depth, they're changing pressure. And so their environment is obviously having an impact on the organism. And so one of the ways they deal with this is they have a bladder. And a bladder is just a sac. Okay, so they have a gas bladder that will change with the different depths. Okay, so that gas bladder will either release gas or hold on to gas to help equalize the internal pressure so that they can deal with the constantly changing pressure in their environment. We're also going to talk about what's called an introduced or a non-native species. Sometimes it's called an invasive species. So obviously these are going to be part of the environment, and they have a huge impact on the native population. So these introduced species, these non-native exotic species, they have no predators because they're not natural to the habitat. So they have no predators. As a general rule, the parasites and occasionally the pathogens that are there as well do not affect them. So these are all things that would normally limit their population. Okay? And so with an introduced or an invasive species, you have this population come into the environment that has no predators. It doesn't really get sick. It basically doesn't have any of the things that would normally limit a population size. And so now they are preying on the native species. So they're reducing their population, and a lot of them are able to outcompete the native species. So So they're winning the competition there for resources against the native species. So now the native species doesn't have as much food, it doesn't have as much shelter, not as much water available to it, because these organisms are basically taking over. And their population